Good afternoon, everybody. This is Bob, K5CRX for the McKinney Amateur Radio Club. We're continuing with our general prep class here. This is session number 3 of the class. Tonight we will be covering receivers and looking forward to going through that with everyone. And hopefully everyone will come away with a better understanding of receivers, plus knowing some of the answers on the test. We'll start momentarily. Okay, so as I was saying, we're on the receiver section, and we cover that I think pretty good on that, and then transmitters next time. The way Gordon West arranges the material is totally different from the way ARRL does it. ARRL does it by groupings of the questions, where Gordon West does it more by subject matter. So that's why we're calling it receivers and then transmitters. He's pulled the questions that have to do mainly with receivers into one slide presentation, and likewise for transmitters. So that's kind of the reason we're doing what we're doing here with that particular thing. So, excuse me. All right, and I'm going to go to another window now. Go to that one and that one, and we're going to share that one. And we're going to share. Nope, that's not it. That one. Share. Full screen. Okay, are you seeing the screen now?
Yep, we got it.
Okay, good. Okay, so I'm going to this is the Gordon West, taking this one from the top because he covers a lot of good information, and I think it'll be good for us just to go through these things, not real fast, but kind of quickly, and talk about some of the stuff that's there. As before, if you have any questions as we're going along, please just yell at me here and say, "Hey, what about this?" And we'll stop and talk about it. So anyway, we're focusing on receivers again. Sensitivity is a term often misused to describe a receiver. It gets some bad rap sometimes. A high gain amplifier amplifies noise as well as the signal that we're looking for. So a good receiver would have a way to try to suppress that noise a little bit. Nonetheless, all the different pieces that work together, a bandpass filter, a noise reduction circuit, and all that help to make a good receiver. Intermodulation, mixing of two different frequencies to produce another frequency or more than one. And that's just one of the things that we talk about. Intermodulation is both good and bad. We use intermodulation to give us a frequency we want. And then it can also generate frequencies that we don't want that cause a problem for us, which we'll talk more about a little bit later. The word superheterodyne is an interesting $5 word. It came to use back in the late 30s, early 40s. It was a new technique of receiving signals off the air. Basically, we take the signal off the air, mix it with another frequency, and this is where the intermodulation thing comes in. We mix the incoming signal with another frequency, and then from that, we will get the two original frequencies plus the sum of the two as a frequency, and the difference between the two as the fourth frequency, as well as some harmonics that go with all of that. So from that, then we will take the desired signal that we want, which is usually the difference, which is usually 455 kilohertz or 10.7 megahertz. We'll take one of those two frequencies, feed it into a filter circuit, and pull that out. We call that the intermediate frequency, or the IF. And then we have a lot of selectivity we gain out of that, actually, and amplification and so forth. And it goes on through the receiver circuit to get what we want out of it. But intermodulation is just the mixing of two different frequencies to produce other frequencies. And in the case of doing the IF thing there, we want that to happen. Now, if it gets carried away and other signals get involved in there, then it can cause all kinds of receiver performance problems. So you hear all kinds of things and birdies and all kinds of other crap that we don't really want to hear. Okay, next. Applying two or more signals to a nonlinear device, and that's one of the keys in the question, a nonlinear device. One can actually have an infinite number of sum and difference frequencies appearing, and all those extra frequencies are garbage, basically. They're stuff that we don't want. You take a simple diode and use that. That's called a square law device, which you don't have to worry about. We get involved in some heavy calculus type math, and the way they figure all that out. Don't have to worry about that, thank goodness, as they say. All you need to know is that with two input frequencies, the products with odd exponents create the signals closest to the original input. And probably when we get to that question, the easy thing is just to memorize the actual answer that goes with that question. Okay, And this is how you would do the subtraction of one frequency from another. I'm not going to actually go into this. I will send you this presentation if you want it, and you can go back and practice with this if you'd like to. But you don't really need to. There's not that many questions that deal with this. I think there's only one actually, and just remember the answer is C. It's odd. Excuse me. Okay, this is a good one. I like this one. This is a block diagram of two different kinds of receivers. The top, they're calling a generic receiver. I would call it a single conversion receiver, but that's just my personal terms, versus the bottom diagram, which is a dual conversion. What this means is we're going to take the RF input from the antenna. We're going to mix it one time with an oscillator signal, and we're going to get that intermediate frequency or IF signal. It's going to come out of there, go into an IF amplifier, an intermediate frequency amplifier, where it gets boosted, made strong enough that we can work with it. Then it goes into a detector circuit of some kind, which converts that RF or extracts from that RF the audio that we want to hear, which then goes to an audio amplifier or baseband amplifier, as they call it, and goes out to the speaker or headphones or whatever you have hooked to it. The key here, the generic, is it only has that one mixer. It only goes through one IF frequency, versus the dual conversion gets converted twice with two different IFs. First and second IF. So we start off on the left-hand side. The antenna signal comes in. We amplify it a little bit, mix it with a local oscillator, and then take that, and that will give us another frequency besides the original that we're going to work with. We'll run that through the first IF amplifier, build it up a little bit. Then we'll mix that signal with yet another oscillator signal to get yet another intermediate frequency signal, which then we will process, send out, and detect it, and then put it out to the speaker. So the frequencies most commonly used for that, just to make it, hopefully it makes it make more sense. The first IF, that on the left there, that first mixture, P1, P2, and P3, that first frequency coming out of there usually is 10.7 megahertz. And there's a reason that that's chosen. We won't go into that right now. And then the first IF amplifies the 10.7 megahertz, which carries all the information, all the intelligence from the signal that came through the antenna. Then it gets mixed down again to 455 kilohertz for the second IF. And again, there's a reason for using the 455. And then it gets amplified, detected, and we are able to see that. Any questions on the diagram and the kind of a general quick layout of how receivers are laid out? Okay, here we go. And they say the aforementioned double balanced mixer. I'm not sure what they're talking about there, but at any rate, a double balanced mixer is another circuit component that's not really spelled out in that diagram. Anyway, it's used to detect the signal for a single sideband receiver. It basically extracts the intelligible audio from the single sideband signal that comes in. So, and it can be used both in the transmitter and the receiver, but in this case, we're talking about it from the receiver's standpoint. Key being double balanced mixer equal single sideband. We apply the intermediate frequency to one port of a detector and a beat frequency oscillator, which is an audio oscillator, to the second port, and the output on the third port then gives us the demodulated audio or the signal that we really want to listen to. The key here, though, is product detector, single sideband. Heterodyne. We mentioned super heterodyne a while ago. Heterodyne comes from a couple of Greek words there, basically meaning we're doing something different to make some good work out of it. We have two voltages going into a mixture of some sort, and from that, we'll get two new frequencies out of that mixture, the sum of the two inputs and the difference between the two, and we also get the two original frequencies also. So we have four frequencies that come out fairly strong from a mixer, and one of those will be the IF frequency that we're looking for. The heterodyne circuits used in modern transceivers and still receivers and transmitters to convert frequencies down to something or another where we can actually work with it and bring it down to the point where we can hear it with our ears. Okay, way back in the 30s and 40s, the superheterodyne first came into being. Used a mixer and a local oscillator. Would take the input signal, as you see in the little diagram down there. Signal A comes in, gets mixed with a local oscillator signal into a mixer, and we take the difference between the input signal and the oscillator signal at 455 megahertz, and we amplify the 455 megahertz. Since it's been mixed, it carries all the audio along with it, and then we can work with that and go on down the line. To get whatever we want as far as the data that signal is carrying. Again, the key there is we use our mixer and a local oscillator signal work together to give us that output frequency that we're looking for, called the intermediate frequency, or the IF. Again, stop me if you have a question. Otherwise, we'll keep moving so we can try to finish on time. Okay, DDS is another term we get into, direct digital synthesis. What direct digital synthesis is, essentially, it's a crystal controlled oscillator. By being crystal controlled, it's going to have a very, very accurate frequency control. It's going to vary very, very little, which is very critical when we're doing, especially doing digital work, where we need to be at a specific frequency. Then we take that signal that comes out of that crystal oscillator, and using some digital circuits, we divide and multiply and mix and do all kinds of crazy things so we can get whatever frequency it is we want out of that thing. And generally, you can go all the way down to 1 hertz. You can go 1 megahertz, one megahertz plus 1 hertz, and right on up the line, which again is good if we're doing FT8, digital type operations where you need to be very precise. Key there being a variable output frequency with a stabilized crystal oscillator is what makes that thing work. Direct digital synthesis, DDS. Software-defined radios. This is new for the general test. Okay, it basically does the same thing as our standard old analog receivers always did before, but it throws digital signal processing in to help us out with what we get out that we can hear. The first thing it does, it takes that RF signal from the antenna and takes a sample of it. It samples the signal, as we call it, taps into the signal, and then it converts that into digital data. Then we can manipulate the digital data. The signal is now in the time domain, so if you looked at it on an O-scope, you'd have time running along the horizontal axis, which is what time domain means. So we run that thing through the digital system. We can filter it, detect it, modulate it, demodulate it, whatever we want to do, as they say, using cheap silicon-based number crunching, i.e. using transistors and integrated circuits and all the different things that we have to make those ICs work. After processing, then it goes back to analog again, which is what we need so we can hear it. And then we can either hear it or use it for whatever it is we're trying to do with it, data or something that we listen to. IQ is another crazy thing. The I and the Q are inputs into a circuit. The I stands for an in-phase signal. Q stands for a quadrature or 90-degree phase shifted signal. The key here is Q stands for quadrature or 90-degree phase shifted. That's the answer to the question. 90 degrees is the key. Basically, we use this in frequency modulation detection, FM detection, all the different frequency shift methods. Generally can respond to an IQ demodulator. And this is kind of a repeat from before. In the superhet, well, the combinations give us the sum of the different frequencies plus the local oscillator and the RF input frequencies. There are 4 frequencies out. However, there's only one that we want, and that'd be the IF frequency. Then there's one we don't want called the image frequency. The higher the IF frequency is, the farther the image is removed from the desired signal. That is, it's not the one we want. It's the highest of all the 4 that's generated, is the one we don't want. And that's called an image frequency, and that's the one we don't want. And then in order to get rid of that, oftentimes the dual conversion receiver will help take care of getting rid of those image frequency or do image rejection. Okay, in strong signals areas, we may have too much signal coming in, that it would cause some craziness in our receiver, and that image response can be so strong that it can actually interfere with the IF signal that's coming in. So that can happen. We have an attenuator circuit on the front of most receivers where we can actually attenuate the input signal if we need to shut it down a little bit so it's not so strong. We can actually solve that problem that way. Digital signal processing, or DSP. is great because of its flexibility. Most of the digital circuitry is controlled by software, and oftentimes that can be upgraded or changed or modified. And in most cases, the user can modify those things on the fly. So we can make a sharp cutoff filter, a smooth cutoff filter, a notch filter, most any kind of filter we want, just by telling the software controls how we want that filter or that digital signal processing filter, how we want it to respond to us. Key there is it will give us a wide range of filter combinations to help us get what we want, so we hear what we want to hear and not all the other garbage behind it. Can also get rid of noise. Can also do notch filtering and equalization and expansion to make it sound bigger if we wanted to do that. Okay, they're not without their drawbacks, however. On DSP, if you've ever played with it, especially in the HF world, and you turn up the filtering too high, then the audio coming in gets starting to sound like single sideband. It sounds like Donald Duck. It gets really severely distorted, and it's really hard to understand. So there's a balance there between turning the thing up where it kills the noise, but not turning it so high that it messes up the audio so that you can't hear it. So it doesn't distort so bad we can't hear it. It can also generate what are called artifacts. Normally those are little, what we call birdies, little beep beeps, that beeping tones that will show up along the frequency band. We can sometimes filter those out, but not always. It's not a silver bullet, but it certainly works and does what it's supposed to do. We just have to be careful and not overdo it and turn the filter up too high. Okay, block diagram of digital signal processing. Analog signal comes in, gets converted to digital, goes through the signal processor, comes back out of there as a digital signal still, but it's been modified, and then goes into a D to A converter, a digital to analog converter, to convert it back to analog, and then we take that analog signal out and amplify it to listen to it, or pull digital data out if we were doing something with digital stuff, tones, whatever. We can pull that information out as audio analog information. Okay, pulse type noise, usually generated by a vehicle ignition. If you have pulse type noise, when you speed the engine up just a little, rev the engine just a little bit, you'll hear an idle will be going pop, 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 pop. You speed the engine up, and that pop, pop increases pop, 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 as the engine speeds up and slows back down again. Yeah, that's a typical pulse type noise that's out there. We can reduce that by reducing the receiver gain during just the time of that noise pulse. So we don't amplify the pulse, is what we're after. So that's called a noise blanker. While the noise blanker will reduce the pulse noise that's there, it does not reduce the other kinds of noise, the white noise or the hash or the background noise that we hear otherwise. Okay, a notch filter, I'm not going to talk about their example that they talk about here too much, but a notch filter basically is a filter that creates a notch in the signal that's going through the IF system. It will notch out, as we call it. It's something that we don't want. For example, that whistle. We can notch that filter out, so it just filters it out. Likewise, if we're listening to a frequency and somebody is transmitting very near that and they're interfering, we're hearing that too badly, a sharp notch filter can notch out that one as well, so we don't hear it. We'll still hear what we want to hear fairly well, but we won't hear the interfering signal. Notch filters today are almost always digital. In the old days, they were actually mechanical, but that's time past. Okay. The attenuator we mentioned a little bit earlier. The attenuator is good to reduce an overload if you get strong incoming signals. You have something coming in that's so strong it's overloading everything. You can turn that down a little bit so that you don't hear hear such a strong signal and hear the overload and the garbage that goes with it. S meters. S meters measure received signal strength. I guess that's no great surprise, is it? And this is where they give you a little experiment to play with it. We're not going to go through their little experiment. An S meter change from S8 to S9 is an increase of a single S unit. So we go from S1 to S2 to S3 up to S9. And then after S9, we have plus 20 dB, plus 40 dB, and plus 60 dB on most units. dB being the decibel, a relative signal strength indicator. But to go from S8 to S9, 1 unit is a 6 dB increase in the transmitter power or the signal coming in, which is 4 times the change. 3 dB is times 2, 6 dB is times 4, 9 dB is times 8. You get the idea with that. It's not a linear thing in decibels there. It's what's the word I'm looking for? It'll come to me in a minute. Anyway, it's not a constant linear signal, but it's a different sharp rising signal. It's the 2, 4, and 8 with the dBs. Okay, we get to the 20 over S9 is 100 times strong. The signal is 100 times stronger than one coming in at S9. Logarithmic, that's the word I was looking for. These signals are logarithmic. They rise very, very rapidly. They're not linear in the way they rise. Okay, S meters generally are calibrated loosely. They're not generally calibrated all that great, but they are calibrated. And we already talked about the 6 dB, which is the main thing. Okay, now we're down to going through the questions. There's our receiver diagrams. Before we jump into the questions, any questions or any thoughts that you've got before we hit this thing with both barrels? Okay, nothing heard. And we've already covered that, so I'm not going to take the time now to go back over that again. All right, which parameter affects receiver? And I've got my little thing in the way here where I can't see what I'm doing. Let me move it. Which receiver parameter affects sensitivity? Anybody want to guess? Anybody? Come on, it's safe.
The receiver, it's the input amplifier gain, right?
Come on here, machine. There we go. All of them.
Yeah, I wondered.
Amplifier gain, the demodulators gain bandwidth, how much it can pass, and the input amplifier itself. If the input amplifier is generating a lot of noise, that will cause you not to be able to hear things because of the noise that's come in because of it. That's essentially what they're saying with that. Okay, so all of the above. All righty. What process combines two signals in a nonlinear circuit to give unwanted spurious outputs? What's the bad stuff? It's called intermodulation. Now, intermodulation can also be good. The key to this one is the unwanted spurious outputs. It's good when it produces a frequency we're looking for. It's bad if it produces spurious outputs. And I put a little extra text in there about the heterodyning. We've already talked about that one, so I'm going to move on from there. Which intermodulation products are closest to the original signal frequencies? You remember I said this is one that's best just to remember it? Odd. And then there's ways to go about that. I talked a little bit about harmonics. This is just a quick note. We talk about harmonics all the time. There is no first harmonic. For what we would consider the first harmonic is actually the fundamental or the original frequency of concern. Then the second harmonic would be twice that. Third harmonic would be 3 times that, etc. The first harmonic is the fundamental frequency or the starting frequency that we started out with. Okay. Despite all the complex math involved, we talked about this before, that the answer is C. You can go through that if you want to. I don't necessarily recommend it. I did put some information in here about how we deal with second, third, fourth order harmonics. You'll recall that when things go into our mixer, frequency 1 and frequency 2, coming out of that mixture, there'll be the original frequencies, F1 and F2, plus the sum frequency and the difference, the sum of the two and the difference between the two. And when we do that, F1 plus F2 and F2 minus F1 is called the second order harmonics, or the second time up. Then if we double the first frequency, keep the second frequency the same, we do that again, called the third order, and you can see where that's going. Then we double the second, double both frequencies, then we triple the first frequency, and then next time we would triple both frequencies, etc., to go on down through the orders of harmonics. That's mainly, I don't think that's on the test that you need to know. The main thing you need to know is that one right there. If it's odd, 2 minus 1 is 1, that's odd. That's, if that helps any to remember it, I don't know. Just C is the right answer. Product detector is used to, remember what product detectors were related to? Single sideband and CW. In their question, they're only asking about single sideband. Uses a product detector to pull the audio out of it. Another term for mixing two signals, That's where the heterodyning came in before, two different mixing signals coming together. It's called heterodyning. Super heterodyning was a fancy term used for sales more than anything else when they came out with that system of circuitry back in the late 30s and early 40s. Which mixer input is varied or tuned to convert signals of different frequencies to an IF. This is where we take the input frequency, mix it with a local oscillator, and we get an output frequency coming out of it. Which mixer input? You got two inputs, input signal and local oscillator. And the one here is local oscillator. The local oscillator mixed with the input signal gives us an IF frequency, or intermediate frequency, or an IF. Which of the following is a characteristic of DDS, direct digital synthesis? Boy, it's hard for me to say that thing. Anybody want to take a guess at that one? That one should be pretty easy.
Variable output frequency with the stability.
You got it. That's it. The crystal oscillator that backs that up is the key to that thing. That's what keeps it stable. Which of these functions is performed by software in a software-defined radio? What all can an SDS or SDR radio do? It can filter, yes. It can detect the signal if it's told to do that. It can modulate it if it's built into a transmitter. So everything is correct on that one, all three. Quadrature modulation. Talk just a tiny bit about that. We talked a little bit about the I and the Q. This is actually from the ARL slide deck. They're showing a diagram of an IQ modulator. I is the input signal. Q is the phase shifted signal. A Q meaning 90 degrees phase shift. So we take one of the signals in at the top, another signal in at the bottom, mix it with a local oscillator, phase shift one of them, put those together to get an RF out from that particular circuit. Okay. And then there's some notes about this. Okay, it can combine, can do all kinds of things with modulation. The combiner is the part that puts the two together. Using software-defined radios replace a lot of other components that we would normally have in the analog style world. It can do filtering, modulation, detection, and so forth. We talked about that really already. And so you can guess what the next question is going to be. What's the phase difference between I and QRF signals in software-defined radios? What is that phase difference we're looking for? This doesn't change, thank goodness.
90.
You got it. Okay, a note there tells you that all over again. What combination of a mixer's local oscillator and RF input frequencies is found in the output? And they're only giving you two of the four. We mentioned there are four. The mixer's output, you have the original frequency, the two frequencies, plus you have, what are the other two?
Sum and difference.
Exactly. So we have the original two frequencies plus the sum of the two frequencies and the difference between the two frequencies coming out. What is the term for interference from a signal at twice the IF frequency on the desired signal? When it creates an image of what you're actually wanting to see and it gets in your way, that image is in your way. So what do you think the response is?
Image response.
You got it. Bad image. Okay, same thing we looked at a while ago, digital signal processor. Which the following is an advantage of DSP compared to analog? What can we do with a DSP filter that we can't do with an analog filter? Any guesses?
Get a wider range.
That's it. With you can do all kinds of things with the different bandwidths and the different shapes of the filters and all that. You can do by just rotating a couple of knobs. What happens as the receiver's noise reduction control level is increased? Now, what they're saying here is when we're dealing with the receiver's digital signal processor and we crank up the noise reduction to try to filter that out, if we crank it up too high, what happens to the quality of the audio?
Becomes distorted.
Exactly. How does the noise blanker work? Anybody?
reduces the gain by, no, it redirect,
No,
You were on there about by reducing receiver gain
yeah, reduces the
during
gain
the
during
noise pulse. While that noise pulse is there, we have a very fast acting diode usually that chops that gain down so that that pulse does not get amplified. Back in the old days of CB radios, ignition noise was a big deal, and instead of using fancy gain reducing circuits like we do now, which are more effective, we actually just put a diode across the audio. The diode would clip the noise peak so it wasn't so high. It was pretty elementary back then. But now we reduce the gain during the receive. Okay. Purpose of a notch filter. And there's a picture of that at the bottom. Let's see now. Can you see my mouse okay? Right there. Can you see me moving the mouse?
Yes.
Yeah.
Okay. All right. So the pass band, what this filter is going to allow to go through goes from the left to right all the way down. And then somewhere along in here, we get a receiving station that's right next to where we really want to receive. We can move this notch back and forth, left and right with software controls. So we move that notch, put a notch right over that offending signal to filter it out. And then everything on either side of that notch still comes right on through. The pass band is still open and it works just fine. That's a notch filter. Okay. Now then. Purpose of a notch filter as found on many HF transceivers is
C.
Think about that again. That's impulse noise. What does impulse noise? That's where we reduce the receiver gain. We want to reduce interference from a carrier that's too close to us. Oops. Come on. Come on. There we go. I just realized when I use the mouse, it messes up my slide clicker. Anyway, to reduce interference from carriers that are too close to us, that are within its passband, it just lets us notch it out, is what we call that. And it might not be a carrier, it could be a whistle, it could be any kind of little interference that happens to be there that's in our way. We can notch that out so we don't hear it. What's the purpose of using a receive attenuator? Why do we attenuate the input of the receiver? To do what?
Prevent from overloading on incoming.
Exactly. Prevent overload. That's it in a nutshell. What does an S meter measure?
C.
You got it. What kind of signals coming in? Is it extremely accurate? No. It's relative. It just gives us an idea on received signal strength. Oftentimes, they are, in fact, calibrated loosely at the factory. But generally speaking, when we're looking at the S meter, we don't have anything to compare it to except another signal that we might receive. And we say, this is good, this is bad. Or we give a signal report to somebody and say, yeah, you're coming in S9, or you're 20 over S9 if they're close and really strong, something like that, to let people know that you're receiving them quite well. They're not that accurate as far as accuracy is concerned. They're just there to give us a relative received signal strength. How much power does it have to do? Can't talk. How much power do we need to change at the transmitter to go from an S8 to an S9 to make it go up by 1 S unit?
It's double 2 times the power, right? 3
Close.
dB is.
I think it's 4.
4, exactly. 6 dB.
Yeah.
6 dB is 4. Okay. And then the one about the 20 dB over S9. If we're 20 dB over, that means that thing is a really powerful signal. It's 100 times more powerful. Again, this is where the fact that it's not a linear signal, it's a logarithmic value that we're measuring here. So it rises very dramatically as the signal strength goes up. So 100 times more powerful at 20 dB, 40 dB would be 1,000 times more powerful, 60 times would be 10,000. So it's a real high jump there in those things. Must change to change by 1 S unit. How many dB?
6 dB.
Exactly. All right, and that is actually the end of that. So Wow, we did good, didn't we? What's it? So we got 20 minutes. We're doing good. We can talk about some of those things if you want, or we can go ahead and introduce transmitters if you like. Introducing transmitters would probably be a good idea because it has a lot more slides. What do you think? Are we okay with that?
Yeah, let's go ahead and introduce it.
Okay, then let me file open that one, full screen. That share that one, share it. Okay, are we okay?
Yep.
Okay. And this has the standard stuff introduction to it. Here we go, talking about things. The instantaneous power level of the signal varies with AM, amplitude modulation. What this is saying is on an AM signal, we impose the audio value, in most cases it's going to be audio, on top of a carrier, which is just a sine wave at a given frequency, and we vary the power in that signal up and down. It's called amplitude modulation or height modulation, AM. Balanced modulator, and I've got something here I've got to move. Excuse me just a moment. I haven't figured out how to get rid of that like I'd like to. Balanced modulator is used in both transmitters and receivers as an instrumentation and other things. The balanced modulator, when supplied with an RF carrier and audio signal, produces a double sideband suppressed carrier signal. Okay, and you follow it up with a passband filter that takes one of the sideband frequencies out, and it becomes a single sideband generator at that point. So actually, it's a single sideband suppressed carrier is the technical term. We generally just call it an SSB signal or single sideband signal. Most common implementation for the balanced modulator is the double balanced modulator or DBM. And that's showing a picture of it. The modulating input on V2 would be our voice, generally speaking. And then the carrier input signal will be V1, whatever this carrier is going to be. It goes through the balanced modulator. It goes through its filters, picks up either the lower or the upper sideband by itself, sends it on out to the output where it gets amplified, goes to the antenna, or wherever it needs to go after that. When impedances are matched, we have the greatest amount of power transfer. We've talked about impedances way back when. We talked about antenna impedance is generally considered to be 50 ohms. Our coax feed lines are 50 ohms. So if we can get the antenna to resonate at 50 ohms, it's matched. The two impedances match. Impedance matching transformer will allow us to help that match, and we often do that with a balance type transformer to prevent desired impedance to the transmitter and the feed line. So we can use an impedance matching transformer to offset any imbalance. NF principle of transformers, no free lunch. I'm not sure where that came from, but anyway, properly matched transformer can minimize losses, but you never get more out than you put into it. So there's always some losses when we use an impedance matching transformer. That's essentially what they're saying. The balanced modulator, we talked about this before, produces an upper and lower sideband signal with the carrier reduced near to zero. Upper and lower sideband signals will go into a narrow filter, which cancels out one of the sidebands, the one that we don't want. If we're working on upper sideband, it would filter out the lower sideband. If we were working on lower sideband, it would filter out the upper sideband. And you might remember that in HF, most of the frequencies, generally speaking, the frequencies below 7 megahertz, we use. Let me get it backwards. Watch me get it backwards. I believe. Correct me if I'm wrong. If somebody remembers, and I may have it backward. But anyway, on one of those we use the LSB, and above that we use the upper sideband. The other uses lower sideband. And right now I just went blank. I don't remember which is which. But it's kind of it's not a law. It's just kind of an unwritten operating principle. Okay, so the balanced modulator is going to give us the upper and lower sideband. We'll filter one of them out with a filter, and that's what goes out eventually to our antenna. Phone emission uses the least bandwidth as the single sideband. Now, notice it says phone emission. It didn't say just emission. If they just said emission, it would either be CW or one of the digital systems. Generally, CW is considered the lowest emission. But phone emission with voiceover takes the least bandwidth if it's single sideband. About 2.8 kilohertz of bandwidth is what we're saying. Modern HF ham radio may include an adjustable transmit single sideband filter network that can decrease the amount occupied from the normal 2.8 down to 2.6. Resulting signals sound void of bass response. It's a little bit narrow filter. Can help get it go through if you have a lot of noise in there. It makes the signal a little bit more treble sounding, I guess is a good way to say it, and it will help you to be able to hear it through the noise. Okay, quick block diagram for a transmitter. Microphone over on the left, an amplifier for that to boost up the audio signal. Goes through the balanced modulator. You notice the oscillator, the carrier oscillator down there has upper sideband and lower sideband crystals or controls. So it's generating both. So we come out of there, but then we filter out with another crystal filter, another type of filter. We filter out either the upper or the lower sideband. Then that becomes an intermediate frequency that we're working with. We multiply that, mix it with another signal, boost it further up, multiply that again. Finally, due to the final VFO, which is the variable one that's out there, that lets us get the actual frequency we want to transmit on, gets mixed with the intermediate frequency and goes out to the power amplifier and then out to the antenna. All that stuff going on just by one push of the microphone button. Many of the radios have speech processors. Speech processors can be good or bad. They can help make the signal cleaner, or they can also, if it's like some of the other things, if it's turned up too high, like digital signal processing, turned up too high, it can distort the signal and make it unreadable. A little bit is good, can increase the apparent loudness. It makes it sound clearer, but if you get too much on there, it's going to be a problem. Turn on the speech processor will not increase the PEP output, that peak envelope power output. If you're 100% modulated already, it'll increase the average power, which will tend to make it the sound a little bit garbledy sounding. It sounds hot, sounds like you're shouting into the microphone. So you want to stay off the speech processor button unless you really need it for some crazy reason. Speech processors are a mixed bag, is another way to say that. New high frequency transceiver you're going to reward yourself with has a built-in ALC, or automatic level control. Basically, the automatic level control is there to control the transmit power. In case you try to overdrive it, it should cut it back just a little bit. Most of the modern transmitters have a way to monitor the ALC. It have a meter setting where you can just say monitor the ALC, and you want to watch that ALC meter for and have it set generally for the minimum amount of activity that it can have. If it goes way up into the red, into the danger zone, then you know you've got something set wrong. You're pushing too high. Your mic gain is set too high. You're using speech processing and it's set too high as well. So generally speaking, we want to be real careful. Watch your ALC. It can help make sure that your signal is clean. In my case, I generally just set it for minimum and leave it there. ALC output jack. It also can be tied to a linear amplifier. A linear amplifier is an amplifier, a big heavy-duty amplifier we put on the output of our HF radio. Normally, most of the HF radios will put out 100 watts, generally speaking. And then you can go into an amplifier, which will take that up to a maximum of 1,500 watts, depending on the amplifier. So that amplifier also needs to know what's going on. So the ALC jack feeds the interlinear amplifier that lets the two talk to each other, if you please, provides the handshake when the drive level is set correctly. And with that, it helps to keep the amplifier in check so that you don't distort your signal due to excessive drive and overdrive the amplifier itself. And if you overdrive the amplifier too hard, too long, you can actually damage the amplifier, which obviously is not a good thing to do. If you overmodulate on HF, You're going to spread your signal over a wider bandwidth than a properly modulated HF signal would. If somebody says you're splattering, turn down the mic gain or turn off the speech processor. The splattering says that we're driving too hard, and it causes all kinds of spurious radiations to come out of the transmitter, and it just makes a mess all the way around it. And you might hear it way up higher than you're intending to transmit. So if somebody says you're splattering, you just turn down the mic gain and or turn off the speech processor. Most newer high frequency transceivers have a speech processor button that'll let you turn it on and off, of course. But if you turn it on, you also pick up background noise and other things that you don't want, and it can cause you to splatter if it overdrives. So you want to be careful with that one. Okay, excessive drive set for an AM phone single sideband transceiver, get the sound to be distorted. That's true with just about any of them. Signal waveform shown on the O-scope has the top clipped off. Now, wait a minute here. Wait a minute. Time out just a minute. On an amplitude modulated phone, single sideband transceiver. Okay. Now what they're saying is if you look at the output waveform, instead of being a nice sine wave as it should be, if you whistled into the mic, you would see the tops of the sine waves flatten out, kind of like the little picture they're showing down there. Guys sit in front of an O-scope, and those signals should be nice and round on the top and the bottom, but instead they're flat topped, or the tops are chopped off, which means we're overdriving. Systems need to be linear. That is to say, whatever goes into a system needs to be what comes out of it. We can do a two-tone test on our transceivers, and we look at the output from the transceiver on an oscilloscope, and we can see if those two tones are coming through linearly. That is, if the signal coming out looks like the signal going in, just stronger. So two-tone test is the one that's used to check for transmitter linearity. If you plan to regularly service your own equipment, they make a little box that will actually generate those two tones that need to be generated. They're two tones that are not harmonically related. That is to say, it wouldn't be, for example, like 500 hertz and 1,000 hertz, 600 hertz and 1,200 hertz. It would be something like 700 hertz and 1,300 hertz, something on that order. Okay, sideband is the predominant phone system that we use today. A lot of activity there, but there are still some old AMers out there. Usually the AM, people that operate AM will operate on the top end of whatever band that you happen to be on. That's not a hard and fast rule, but that's generally true. AM sounds totally different from sideband. It has a lot more fidelity to it. The envelope of an AM signal is the outline or extreme outer limit of the RF frequency signal. 100% modulation is when the envelope goes from 0 during the negative peaks, increases twice the amplitude on the positive peaks. In other words, you get a good sine wave coming out of it with no clipping. An O-scope is the best piece of test equipment. If you're going to look at the signal, the O-scope has horizontal and vertical channel amplifiers, meaning that it can spread the signal over the face of the O-scope screen horizontally and vertically, so you can actually see what the signal looks like. Okay, when magazine editors review the waveform of the CW signal or the two-tone test, they would show it on an O-scope, as it shows there on that O-scope at the bottom. Take the attenuated RF output on a transmitter, couple it to the vertical input of the O-scope, and that will allow us to view it on the O-scope. The output has to be attenuated because the input of an O-scope is not made to handle 100 watts. So you can use an attenuator to reduce that signal that you're putting into your into the O-scope down to about 1/10 of a watt or so, generally speaking. And there's all kinds of special heat sinks and other things you can use that will do that RF attenuation. If you're into that, you would have one of those dummy loads that will do that. When you whistle into the single sideband microphone, look at the resulting waveform. You see only an O-scope. You can see that only on an O-scope that can represent the complex voice waveforms we can measure them, which is true. If you're looking at the output of a transceiver on an O-scope and you whistle into the microphone, you will not see a smooth sine wave unless you can whistle on an exact frequency and hold it exactly there with no deviation whatsoever. Generally, we'll see a little bit of extra up and down and a variation in the signal, but you can get an idea if your transceiver or your transmitter is reproducing the signal correctly by looking at it on the O-scope. After new tubes have been installed, tubes, yes, tubes. We still use a lot of high power amplifiers. Usually are using tubes these days. So if you have a tube type amplifier and you change the tubes, you have to neutralize them, which eliminates the possibility of self oscillation. The neutralization cancels out some stray capacitance between the tubes grids. And that would normally cause it to self-oscillate, or it would cause it to oscillate when you don't want it to. That's not unlike when you're talking on an audio microphone with a PA system and you walk in front of the speaker and you get that squeal, that feedback. That's what we're talking about. You can actually neutralize that with an audio amplifier as well with special circuitry. But in the amplifiers we use, they have special neutralization circuits to eliminate the self-oscillation or the oscillating when they are not supposed to. Modulation that changes the frequency of the output signal is called FM, or frequency modulation, meaning that we're varying the frequency in step with the input signal. The two things that they're showing there, the top one is the information signal, just an audio sine wave. The carrier frequency, which is just a straight frequency going through. If it were amplitude modulated or height modulated, it would look like the third one there. As you can see, as the sine wave goes up and down, the height of the carrier goes up and down in sync with it. However, for FM, you'll notice the height stays the same all the way across, but the frequency itself changes in sync with the modulation. You'll notice that sine waves get closer together or farther apart depending on the frequency that's being input into it. In an VHF-FM transmitter, a low-power oscillator operates at HF levels. It's the job of the multiplier to select a harmonic of the signal to produce the desired operating frequency. We're back into heterodyning, frequency mixing, and all that stuff. That's essentially what we're saying. For a VHF transmitter, which is the 141, come on, brain, get in sync, 144 to 148 megahertz. We don't have a local oscillator that generates a frequency that high. So it generates a lower level frequency, usually in the HF range, below 30 megahertz range. And then you multiply that up by selecting one of the harmonics and amplifying it until you get the frequency that you want. Okay, let's see. Calculate this answer by multiplying 2 times the sum of the deviation of modulating frequency. Okay, in FM, we have a thing called deviation that we measure. Deviation is how much can we vary that output frequency of the transmitter. 5 kilohertz deviation is generally considered standard or maximum for most of our FM things that we do. So they're saying here we have a deviation of 5 kilohertz. We have 3 kilohertz of audio modulating that. The two together gives 8 kilohertz. 2 times 8 is 16 would be the total bandwidth for the FM phone transmission. That's just a little thing you just kind of have to memorize, I think, probably more than anything else. And they're special equipment that will actually measure FM deviation and all that sort of thing. And okay, it just hit 8 o'clock. I guess that's a good place to stop. So let me stop that one and go back to where we came from. Stand by just a moment here. Come on, be nice. Okay, sorry guys, I'm not a good operator of this thing, I don't guess. And that we will stop there for tonight, and we'll pick it up again next time there and go on through that. And maybe if you have any questions in the meantime, make a note of it, and we'll be more than happy to kick it around and talk about it. I'm trying to give some of the practical sides of this stuff as we go through, which is pretty much ad lib, as you can tell, but some of the common things that we see in operating day to day. So that's it for this time. I hope to see you again next week, and we'll do some more of this. is, as they say, same bat channel, same bat time, same bat station. We'll see you next week.